Welcome. Let your shoulders drop and let your breath find its own slow rhythm. There is nothing to do now but rest and listen. Tonight we drift outward through the galaxy that holds us, beginning right where you are. Earth completes one full circle around the Sun every 365 and a quarter days. That small fraction is why, every 4 years, a single extra day slips quietly into February. Earth sits inside the Milky Way's Orion Arm, a modest ribbon of stars threaded through the galaxy's vast spiral. This arm is not one of the galaxy's grand structures, but a quieter branch tucked between larger ones. Our entire solar system rides along inside it, carried gently through the dark. From here, the galaxy's brighter arms glow like distant shores. The Sun rests about 26,000 light-years from the galactic center, roughly halfway out toward the galaxy's edge. That distance is so vast that light itself, the fastest thing there is, needs 26,000 years to cross it. We are neither at the heart of the Milky Way nor at its outer rim, but somewhere calm and in between. Our solar system takes about 230 million years to complete one full orbit around the galaxy's center. In that single galactic year, continents have drifted, oceans have risen and receded, and life has slowly changed shape upon Earth. The last time we were in this same position, dinosaurs had not yet appeared. We are still, even now, partway through that long, unhurried circle. The Sun moves through the galaxy at roughly 220 kilometers every second, carrying Earth and all its companions along with it. Despite this tremendous speed, nothing about our daily lives feels different. The motion is smooth, steady, and utterly silent, like a boat gliding across still water. We are always traveling, even while sitting perfectly still. Alpha Centauri stands as the closest star system to our Sun, a gathering of stars bound together by gravity. It lies just over 4 light-years away, nearby cosmic standards, though still impossibly far by any measure we use on Earth. A spacecraft traveling at ordinary speeds would need tens of thousands of years to arrive. Even so, its light reaches our night sky freely, unhindered by the distance. Proxima Centauri is the single closest star to our Sun, a faint red dwarf tucked within the Alpha Centauri system. It glows dimly, far cooler and smaller than our own star. Around it circles a small rocky world, quietly orbiting in the hush of that distant light. Proxima reminds us that nearness, in the galaxy, still means unreachable. Most of the Sun's nearest stellar neighbors are faint red dwarfs, small and cool compared to our own star. They shine with a gentle, reddish light that never overwhelms the darkness around them. Though common throughout the galaxy, they remain invisible to the naked human eye from Earth. The galaxy's true population, it turns out, is quieter and dimmer than the sky suggests. The Sun sits within a low-density region of space known as the local bubble, a vast cavity carved from interstellar gas. Inside it, the space between stars is thinner, emptier, and unusually clear. This bubble stretches for hundreds of light-years in every direction around us. We have, in a sense, made our home inside a great open clearing. The local bubble was carved by ancient supernova explosions, stellar deaths, that occurred millions of years ago. Their expanding shock waves pushed gas outward, hollowing out the quiet space we now drift through. What once was violent and bright has settled into something calm and clear. Even the Sun's peaceful neighborhood carries traces of that old, distant fire. Let your breath settle into its own slow rhythm now. Notice how each exhale grows a little longer than the one before it, releasing more of the day with every release of air. There is nothing to arrange, nothing to hurry. Let the next inhale rise on its own, and let the next exhale carry a little more weight from your shoulders, your jaw, your hands. Rest inside that widening pause between breaths. Barnard's star, drifts quietly through space, one of the nearest stars to our Sun, about 6 light-years away. It is a small red dwarf, ancient and dim, invisible without a telescope. Astronomers have tracked it for more than a century, following its unusually swift motion across the sky. Though close by galactic standards, its light remains far too faint for human eyes to notice. Sirius shines as the brightest star in Earth's night sky, a brilliant blue-white point above the horizon. It lies about 8.6 light-years away, paired with a faint white dwarf companion hidden in its glare. Ancient civilizations tracked its rise to mark the turning of seasons. Its brightness comes not from unusual power, but simply from how near it sits to us. The Pleiades cluster gathers a few hundred young stars in a soft, close huddle about 444 light-years from Earth. To the naked eye, it looks like a small hazy patch, though a telescope reveals dozens of blue stars veiled in faint dust. Cultures across the world once traced their own stories into that tiny formation. Overhead, on clear autumn nights, it drifts along its own slow arc. Within the constellation Orion lies a nursery of stars, glowing about 1,350 light-years away. Clouds of gas and dust there collapse slowly into new suns, lit from within by young, hot stars. Visible even to the unaided eye as a faint smudge, it holds thousands of infant stars, still wrapped in their birth clouds. It is one of the nearest places in the galaxy where creation is still quietly underway. Encircling our quiet corner of space, dense molecular clouds mark the edges of the local bubble. These clouds, thick with gas and dust, rise like walls around the emptier region we inhabit. Beyond them, star formation continues in colder, denser pockets of the galaxy. Our own neighborhood remains a clear space, bordered by these darker, heavier reaches. The Gum Nebula spreads faintly across the southern sky, the remnant of a supernova that exploded long ago. Its glowing filaments arc gently over hundreds of light-years, thin traces of an ancient stellar death. Radiation from nearby young stars keeps the gas softly luminous. It rests near our own region of the galaxy, a quiet neighbor shaped by fire long since extinguished. Near the inner edge of a modest feature called the Orion Spur, our solar system finds its place. This spur bridges two larger spiral arms, a smaller ridge of stars and gas set between them. Astronomers once considered it a minor branch, easy to overlook amid grander structures. Yet from here, the whole galaxy still stretches outward in every direction we look. Orion's arm, home to our Sun, is not one of the Milky Way's major spiral arms. It is smaller, shorter, and less densely packed with stars than its grand neighbors, the Sagittarius and Perseus arms. Astronomers sometimes call it a spur, a bridge connecting larger structures rather than an arm of its own. Even from a modest branch such as this, the view of the galaxy remains vast. A thin, flattened disk holds most of the Milky Way's stars, no more than a few hundred light-years thick in places. Here, gas, dust, and young stars mingle together, tracing the spiral arms that wind through the galaxy. This slender disk holds the Sun and nearly all the stars we see at night. It is a narrow layer of light within a much larger, quieter structure. Beyond the slender disk of young stars, a second, thicker layer extends above and below it. This older population drifts in wider, looser orbits, remnants of eras long before the Sun formed. Its stars tend to be dimmer, redder, and richer in the scars of ancient chemistry. Together, thin and thick disks form two chapters of the galaxy's long life, stacked gently one within the other. Let the weight of the day settle now into the mattress beneath you. Feel your feet grow heavy first, as if they are sinking gently into warm sand. That heaviness rises slowly through your ankles, your knees, spreading upward like a tide moving in. Your arms follow, resting fuller and heavier against the sheets. Even your shoulders release their hold, and your head grows still, cradled and unmoving, wanting nothing but rest. Between the stars, fine grains of dust drift through the galactic disk, scattering and absorbing the light that passes through. Starlight traveling toward Earth often arrives dimmer than it began and tinted redder than its true color. This subtle veiling has puzzled astronomers for generations, requiring careful correction to measure a star's real distance and brightness. The dust itself, though sparse, spans such enormous distances that its effect becomes unmistakable. Measured from top to bottom, the main disk of the Milky Way spans roughly 1,000 light-years in thickness. Compared to its diameter of 100,000 light-years, this makes it remarkably flat, thinner in proportion than a sheet of paper set beside a dinner plate. Stars, gas, and dust all crowd into this narrow band. It is within this modest slice of space that nearly everything visible in our night sky resides. Not far from the Sun, a loose gathering of stars called the Hyades drifts together through space, bound by a shared birth long ago. Its members are young compared to the ancient bulge stars near the galaxy's heart, though still older than the nearby Pleiades. Visible to the naked eye as a scattering of modest points, the Hyades marks one of many stellar nurseries once active in our corner of the galaxy. Such clusters gradually disperse, their stars drifting apart over hundreds of millions of years. Within our own spiral arm lies a striking cloud of gas and dust shaped, by chance, like a familiar continent. The North America Nebula glows with the light of young, hot stars embedded in its folds, its dark lanes carving out coastlines and borders. Photographers have long been drawn to its resemblance, though the shape is simply an accident of gas and shadow. It sits a few thousand light-years away, a nearby landmark in our local stretch of the galaxy. Wherever new stars are born, their fierce light strips electrons from surrounding hydrogen atoms, and the gas begins to glow. This ionized hydrogen radiates in vivid pinks and reds, marking the nurseries where starbirth is actively underway. Such regions often stretch across dozens of light years, illuminated from within by the very stars they helped create. Astronomers use this glow as a signpost, tracing where the galaxy is still actively weaving new light into being. Spiral arms are not fixed structures, carried along like spokes on a wheel. Instead, they behave more like waves of gathered stars and gas, a density wave rippling slowly through the disk. Material moves through these waves, much as cars move through a traffic jam, slowing briefly as they pass through a crowded region before continuing onward. This mechanism helps explain why the arms remain visible and organized, rather than winding tightly and dissolving over the galaxy's long history. Closer to the galactic center than our own modest branch lies the Sagittarius Arm, a broader ridge thick with young stars and glowing nebulae. Its light reaches us across thousands of light-years, filtered through dust yet still bright enough to trace on detailed maps. This arm curves inward toward the crowded heart of the galaxy, hosting some of the busiest stellar nurseries known. From our vantage point, it appears as a luminous band, low along the summer sky. Farther from the center, beyond our own arm, lies the Perseus Arm, a wide and prominent spiral feature stretching across the outer galaxy. It holds star clusters, nebulae, and vast stretches of cold gas, sweeping in a broad curve through the Milky Way's outskirts. Light from its farthest reaches takes many thousands of years to arrive, carrying with it the glow of stars we will never visit. Its presence reminds us how much of the galaxy extends beyond our own quiet neighborhood. Scutum Centaurus Arm ranks among the galaxy's two major spiral arms, a dense ridge of stars sweeping through the inner Milky Way. It carries some of the richest star-forming regions known, threading past the galactic bar toward the outer disk. Astronomers trace its path using infrared light, since visible wavelengths struggle to pierce the dust along its length. This arm anchors much of the galaxy's grand spiral design, a long curve linking inner and outer regions in one continuous sweep. On the far side of the galactic center, the Norma arm curls out of sight from Earth's vantage point. Much of it lies hidden behind the crowded bulge, its stars and gas clouds obscured from direct view. Radio telescopes, able to see through dust, have traced its outline across tens of thousands of light-years. This hidden arm reminds us that entire regions of our own galaxy remain unseen by human eyes, mapped instead through patient listening to radio waves. Somewhere beyond hearing, a low hum settles into the room, rising and fading like a tide that never quite arrives. It might be wind against glass, or a house cooling as night deepens. There's no need to name it. Each time it fades, your breath finds a little more room, your shoulders sink further into what holds you. Let the sound blur at its edges and drift with it, unnamed, until it dissolves into the wider dark. 4 major spiral arms are thought to wind through the Milky Way's disk, based on decades of mapping by infrared and radio surveys. 2 of these arms, Scutum Centaurus and Perseus, appear as bright, star-dense structures. The other 2 carry more gas than stars, harder to trace, but still present in maps of cold hydrogen. Astronomers continue refining this picture, since dust and our position inside the disk make full outlines difficult to confirm. Enhanced star formation, rather than a fixed structure, is what actually defines a spiral arm. Stars drift in and out of these arms as they orbit the galactic center, entering denser regions and later moving beyond them. The arm's glow comes largely from young, hot stars, born within these crowded lanes. Older stars, scattered more evenly across the disk, no longer trace the spiral pattern at all. Passing through a density wave, stars and gas slow briefly, gather together, then continue onward, much like travelers bunching at a narrow bridge before spreading out again on the far side. This behavior keeps the spiral pattern intact, even as the disk beneath it rotates at different speeds. Without this mechanism, the arms would wind ever tighter over billions of years and eventually disappear. Instead, the pattern persists, renewed continuously as fresh material moves through it. 100,000 light-years span the width of the Milky Way's disk, a distance so vast that light itself needs that long to cross it. A beam leaving one edge would still be traveling when it reached the other side, long after any human witness had lived and died many times over. Within that span rest the arms, the bar, and the countless stars we've been tracing. It is a single, flattened wheel of light turning in the dark. New arm segments continue to surface in galactic surveys, small bridges and spurs connecting the larger, better-known structures. A survey completed in the early 2010s revealed a previously unnoticed extension, linking 2 major arms across a wide gap. Each discovery adjusts the map slightly, filling gaps left by dust and distance. The galaxy's true shape is still being drawn, refined a little more with every careful measurement. At the Milky Way's center lies a bar, a dense, elongated structure made of millions of older stars stretched along a single axis. Unlike the graceful curves of the spiral arms, the bar cuts a straight path through the galaxy's core. It formed early in the galaxy's history, shaped by gravitational instabilities in the spinning disk. Many spiral galaxies across the universe share this same feature, a straight spine anchoring their swirling arms. 27,000 light-years mark the length of the Milky Way's central bar, a span greater than the distance separating our Sun from the galactic center. Stars within this bar follow elongated, looping orbits rather than the calmer circles found in the outer disk. The bar's rotation is thought to stir gas inward, feeding material toward the crowded core. It stands as one of the galaxy's oldest architectural features, built long before our sun ever formed. Gas drifting near the galactic core feels the bar's steady pull, funneled inward along its long axis like water finding a channel. This flow carries material toward the crowded central region, feeding future generations of stars. Astronomers modeling this motion describe it as a slow conveyor, patient and continuous. Without the bar's rotation, the center would starve of the raw material it needs to keep building light. Certain stars, called long-period Cepheids, pulse with a rhythm tied directly to their true brightness, making them reliable markers of distance. Astronomers use this pulsing to measure how far away a star truly sits, then plot its position across the galaxy. Chains of these stars have revealed curving patterns matching the spiral arms suspected from other evidence. Each pulse is a small beacon, patiently confirming the shape drawn from countless other clues. Enormous clouds of molecular gas gather in the spiral arms, some spanning hundreds of light years and holding enough material to build tens of thousands of suns. Within their cold, dense folds, gravity slowly draws matter together until new stars ignite. These complexes represent the galaxy's nurseries, vast and mostly hidden from visible light. Long after we're gone, these same clouds will still be quietly assembling the next generations of stars. Let warmth begin at the crown of your head, spreading like sunlight settling into still water. Feel it ease across your forehead, loosening anything held there without you noticing. Let it flow down into your jaw, your neck, your shoulders, each place softening as the warmth reaches it. Continue down through your chest, your arms, your hands, resting heavier with every breath. There is only this slow warmth, moving through you, asking nothing in return. The Milky Way's flat disk isn't perfectly flat at all. Near its outer edges, it bends slightly upward on one side and downward on the other, like a great record slightly worked by heat. This gentle curvature likely results from the gravitational tug of nearby dwarf galaxies passing close over cosmic time. The warp has been mapped using hydrogen gas that traces the disk's true shape, far beyond the visible stars. Even something as vast as our galaxy carries small imperfections shaped by its neighbors. Each year, the Milky Way turns only a handful of solar masses of gas into new stars, a slow and steady pace compared to some distant, more turbulent galaxies. This modest rate has held roughly steady for a long stretch of cosmic history, allowing our galaxy to age gracefully rather than burn through its fuel quickly. Astronomers measure this rate by tracking young, hot stars and the glowing gas around them. It is a patient rhythm, unhurried across billions of years. Dark ribbons of dust trace the galactic plane, blocking the light of countless stars that lie behind them. From Earth, this appears as a dim band cutting through the brighter glow of the Milky Way when viewed on a clear night. These lanes are made of fine grains, remnants of dying stars scattered across the disk over billions of years. They hide as much as they reveal, folding entire regions of the galaxy from direct view. Stars near the Milky Way's center complete their orbits far more quickly than those farther out, since gravity pulls harder where mass is concentrated. This uneven pace means the disk doesn't rotate like a rigid wheel, but instead twists differentially, inner regions racing ahead of the outer ones. Over long stretches of time, this difference has helped stretch and shape the spiral arms themselves. The galaxy turns unevenly, like a slow whirlpool with a faster center and a lagging rim. Radio waves pass through dust that blocks ordinary light, allowing astronomers to peer into regions of the galaxy otherwise hidden from view. Using large dish antennas, researchers have mapped gas clouds, star-forming regions, and even the galactic center itself through this invisible window. What visible light conceals, radio waves quietly reveal, tracing structures no telescope built for optical light could ever see. It is a different way of seeing, built entirely on wavelengths beyond our eyes. Hydrogen atoms scattered throughout the galaxy emit a faint radio signal at a wavelength of 21 centimeters, produced by a tiny shift within the atom itself. Because this signal passes easily through dust, astronomers in the mid-20th century used it to trace hydrogen gas across vast distances, revealing the curving pattern of the spiral arms for the first time. This discovery gave humanity its first real map of the galaxy's shape from the inside. A single, quiet frequency helped draw the outline of our entire home. Deep within the Milky Way's disk lies a great swelling of stars called the galactic bulge, a dense central hub where light gathers thick and bright. It occupies the very heart of our galaxy, cradling the black hole and countless ancient suns. Compared to the flat disk around it, the bulge rises outward and upward, a rounded mass of stellar light. Everything else in the galaxy circles this crowded core. Viewed edge-on, the bulge does not form a simple sphere, but takes on a peanut-like or boxy silhouette. This unusual shape emerged as stars interacted gravitationally over billions of years, buckling the structure from within. Astrophysicists studying similar galaxies elsewhere have confirmed that such bulges are common among barred spirals like our own. The bulge, seen from the side, looks almost like two lobes pressed gently together. Many bulge stars formed long before the Sun ever ignited, carrying within them a memory of the galaxy's early years. Their ages, measured through careful study of stellar populations, tend to exceed those of stars scattered across the outer disk. This makes the bulge something like an ancient library, holding records written in starlight rather than pages. Time moves differently there, layered with epochs long past. Not every star in the bulge shares the same chemical story. Some are rich in heavier elements forged through generations of stellar death and rebirth, while others remain metal-poor, closer in composition to the galaxy's earliest days. This mixture suggests the bulge grew through more than one process, blending stars born locally with others drawn in from elsewhere. Diversity, it turns out, lives even at the galaxy's crowded center. Somewhere behind these thoughts, a candle burns low in a dark room, its flame narrowing to a single steady point. There is no need to watch it flicker or fade. The wax pools slowly at its base, and the light dims by degrees so small they cannot be measured, only felt. Let your breathing follow that same unhurried dimming, each exhale a little softer than the one before, until the glow inside you settles into rest. Hidden among the bulge's crowded stars, distant worlds occasionally reveal themselves through a phenomenon called microlensing. When one star passes precisely in front of another from our vantage point, its gravity briefly bends and magnifies the background light, sometimes betraying the presence of an orbiting planet. Survey teams scanning these central fields have found exoplanets this way. Tucked deep within the galaxy's oldest neighborhood, even in that crowded core, small worlds quietly persist. From end to end, the Milky Way's bulge stretches across roughly 10,000 light-years, a vast swelling compared to any scale we know on Earth. Light leaving one edge would take 10,000 years to reach the other, journeying the entire time through crowded starlight. Such distance is difficult to hold in the mind, yet it forms only a small fraction of the galaxy's full width. The bulge is immense, and still it is only the beginning of the galaxy's true size. Out in the disk, stars trace calm, orderly paths around the galactic center, moving together in near-circular harmony. Within the bulge, that order breaks down. Stars there follow orbits shaped more like tangled loops, crossing paths and drifting at varied angles, influenced by the crowded gravity around them. It is a livelier kind of motion, chaotic yet stable across the ages, a crowded dance without a fixed rhythm. Certain pulsing stars, called Aurer-Lyra variables, serve as reliable markers of the bulge's oldest population, brightening and dimming with predictable regularity. Their rhythmic light allows distances to be measured with unusual precision, tracing the bulge's shape from within its dust-shrouded heart. Wherever these stars are found, ancient history is written alongside them. They blink like slow beacons across an otherwise hidden landscape. At the very center of it all, a nuclear star cluster gathers, an extraordinarily dense knot of stars surrounding the galaxy's supermassive black hole. Packed far more tightly than stars anywhere else in the Milky Way, this cluster forms a luminous core within the larger bulge. It marks the innermost boundary of ordinary stellar structure, the last crowded threshold before gravity's deepest well takes hold. Here, the galaxy gathers itself into its smallest, brightest point. Densely packed beyond ordinary comparison, the nuclear star cluster ranks among the tightest groupings of stars ever observed. Millions of stars occupy a space that elsewhere would hold only a handful. Their light blends together into a single luminous haze when viewed from afar. Astronomers studying such density find few other places in the universe to compare it to. This cluster forms the innermost stage before the galaxy's deepest gravity takes over entirely. Surrounding that dense stellar heart lies the central molecular zone, a region thick with gas far denser than anywhere else in the galaxy. Vast reserves of hydrogen and other molecules drift there, compressed by gravity and turbulence alike. This gas provides raw material for future stars, though conditions make new star birth surprisingly difficult. The zone stretches across a few hundred light-years, a small span holding an outsized share of the galaxy's molecular material. At the true center of the Milky Way sits Sagittarius A, the supermassive black hole around which everything else quietly turns. It anchors the galaxy's gravity, invisible itself, known only through its effect on nearby stars and gas. Radio astronomers first traced its presence through a compact, unmoving source of radio emission. Everything in the galactic core, from gas clouds to orbiting stars, answers to its pull. Weighing in at roughly 4 million times the mass of our Sun, Sagittarius holds an almost unimaginable amount of matter within a surprisingly compact space. Despite this enormous mass, its physical size remains smaller than the orbit of Mercury around the Sun. Such density defies ordinary intuition about scale and weight. Stars nearby feel its gravity keenly, tracing tight, fast orbits around a point they can never approach too closely. In 2022, a global collaboration called the Event Horizon Telescope produced the first image of Sagittarius A's shadow, a dark silhouette ringed by glowing plasma, linking radio dishes across the planet into a single virtual instrument made this feat possible. The resulting image confirmed predictions built on Einstein's equations decades earlier. It offered humanity its first direct glimpse of the region surrounding our galaxy's central black hole. Let the jaw loosen, unclenching without effort, as though it forgot what tension ever felt like. The muscles around the eyes ease, one by one, until the eyelids grow heavy enough to stay closed on their own. Behind them, darkness spreads wide and soft, roomy enough to hold nothing at all. There is no need to picture anything there, just darkness, warm and complete, asking nothing of you as it settles in. Racing around Sagittarius faster than almost any other known star, STRO completes its orbit in just over 16 years. At its closest approach, it moves at several percent of the speed of light, an extraordinary pace for anything made of ordinary matter. Astronomers have tracked its path for decades, watching it swing perilously close before pulling away again. Its motion offers a rare direct window into gravity at its most extreme. Careful measurements of STRO's orbit gave physicists a chance to test Einstein's general relativity in conditions far more extreme than anywhere on Earth. Its path bends and shifts in ways that only relativity, not older Newtonian gravity, can fully explain. Observatories tracking its motion found exactly the kind of gravitational redshift and orbital precession relativity predicts. The result stood as one of the clearest confirmations yet that Einstein's century-old equations hold true, even near a supermassive black hole. Thick curtains of interstellar dust hide the galactic center almost entirely from ordinary eyesight. Visible light scatters and absorbs across the tens of thousands of light-years between here and there, dimming the core to near invisibility. Without other tools, early astronomers could only guess at what lay hidden behind that veil. The center of our own galaxy remained, for most of human history, an unseen place just beyond reach. Infrared and radio telescopes see straight through the dust that blinds ordinary sight, revealing the galaxy's hidden heart in remarkable detail. Longer wavelengths pass through obscuring clouds with little trouble, carrying information visible light never could. Through these instruments, astronomers have mapped stars, gas, and structures once thought permanently concealed. What was once an unseen place has slowly become one of the most studied regions in the entire galaxy. Near Sagittarius A, gravity pulls unevenly on wandering gas clouds, stretching them into long, thin streamers as they pass close by. One such cloud, tracked for years, grew visibly elongated as it neared the black hole's grip. The near side feels a stronger pull than the far side, and the difference tears the cloud apart. Watching this happen has given a rare glimpse of tidal forces sculpting matter in real time. Rising far above and below the galaxy's center, two enormous structures glow faintly in gamma rays, invisible to human eyes, but vast in scale. Each bubble stretches tens of thousands of light-years, forming a shape like a great hourglass astride the galactic plane. They were only found through data gathered by an orbiting gamma-ray observatory, hidden until instruments sensitive enough came along. Their smooth, symmetric form suggests something powerful shaped them long ago. Physicists studying the bubble's shape and energy suspect they trace back to a burst of activity from the central black hole millions of years past. A sudden feeding episode, they propose, could have blasted hot gas outward in twin jets that still glow faintly today. The timing remains uncertain, and no one has pinned an exact date to the event. Whatever caused it, the bubbles stand as a quiet record of something dramatic that has since gone still. Sagittarius A is not entirely silent. Every so often, brief flares of X-ray light burst from the region right around the black hole, lasting minutes to hours before fading. These flares likely come from hot gas swirling just before it disappears past the point of no return. Orbiting X-ray telescopes have caught dozens of these flickers, each one a small, fleeting signal from the edge of an otherwise dark abyss. From the direction of the galactic center comes a peculiar glow at a very specific gamma-ray energy, produced when matter meets its antimatter twin and both vanish in a flash of light. This 511 kiloelectron-volt line has puzzled observers for decades. Its source remains an open question. Possibilities range from dying stars to more exotic explanations involving dark matter. The glow itself is faint, diffuse, and strangely persistent. Near the crowded heart of the galaxy, particles are flung to extraordinary speeds, becoming what astrophysicists call cosmic rays. Shock waves from stellar explosions and the churn of magnetic fields near the black hole both seem to play a part. These accelerated particles stream outward across the galaxy, some eventually reaching Earth after journeys lasting thousands of years. Their origin near the center links our planet, however faintly, to that distant and turbulent place. Notice the breath moving on its own, without any push from you. Notice the exhale growing a little longer each time, a little looser, like a tide drawing back further with every pass. There is no need to follow it exactly. Just let it lengthen at its own pace, drawing the shoulders down, drawing the jaw loose, drawing the whole body a little closer to sleep with every slow release of air. The heart of the galaxy spins faster than its outer reaches, much like the middle of a pinwheel turning quicker than its edges. Stars near the center complete an orbit in a fraction of the time it takes stars far out in the disk. This uneven pace, called differential rotation, shapes much of the galaxy's swirling structure. Over millions of years, it helps stretch and win the spiral patterns we see from afar. Two remarkable clusters, known as the arches and the quintuplet, drift in tight orbits near the galactic center, each packed with young, brilliant stars, both formed relatively recently in cosmic terms, emerging from the dense gas that swirls around the core. Their stars burn hot and bright, some among the most massive known anywhere in the galaxy. Bound so close to the center, they endure gravitational stresses, unlike almost any other cluster. Among all known star clusters, the Arches cluster stands out for how tightly its stars are packed together, crowding a small volume of space with immense stellar density. Within its core, stars huddle close enough that their combined light rivals entire small galaxies. Despite this density, individual stars rarely collide, held apart by the delicate balance of their orbits. It remains one of the most striking examples of concentrated starlight found anywhere in the Milky Way. Magnetic filaments stretch across the region near the galaxy's center, long threads of charged particles bent into graceful arcs. These structures span dozens of light years, invisible to ordinary sight but luminous in radio wavelengths. Their curved shapes trace fields threading through the core like combed strands of silver. Nothing about them feels disordered. Each filament runs in a long, patient line, shaped by forces too vast to hurry. Compared to the blazing cores of distant active galaxies, the black hole at our center stays remarkably subdued. Sagittarius, a star feeds on only a trickle of gas, producing a faint glow rather than a roaring beacon. Active galactic nuclei elsewhere can outshine their entire host galaxy. Ours barely stirs. Astrophysicists studying this contrast suspect our galactic center is simply resting between more turbulent eras. Stellar winds, pouring from massive young stars near the center, carve delicate arcs into the surrounding gas. These winds, streams of charged particles racing outward, push against clouds of dust and hydrogen. Where wind meets cloud, glowing curved structures form, resembling long luminous ribbons frozen mid-motion. Infrared images reveal these arcs glowing amber and rose against the dark backdrop of the core. A vast halo surrounds the entire visible disk of the Milky Way, an enormous sphere far larger than the swirling spiral we usually picture. This halo holds scattered stars, faint globular clusters, and thin traces of gas. Compared to the flattened disk, it feels almost formless, spread wide instead of pressed into a plane. Light traveling through this outer region has often journeyed for tens of thousands of years before reaching us. Ancient stars drift through this halo, some among the oldest surviving in the galaxy, formed not long after the Milky Way itself began taking shape. These stars carry chemical fingerprints from the universe's early chapters. Their compositions hold little iron, a sign they formed before generations of exploding stars had enriched the surrounding gas. Each one is a quiet witness to a much younger cosmos. Many halo stars follow highly eccentric orbits, swinging inward close to the galactic disk before arcing far back out into the dark. Unlike the calm circular paths of disk stars, these orbits stretch and tilt in every direction. A single halo star might spend eons in an elongated loop, unhurried, tracing an orbit that could take hundreds of millions of years to complete. Far beyond the visible disk, the stellar halo extends several 100,000 light-years outward, reaching distances that dwarf the galaxy's familiar spiral. Few stars occupy this space, scattered thin across enormous volumes of near emptiness. Some halo stars sit so far out that they orbit at the very edge of the Milky Way's gravitational reach, drifting at the border where our galaxy fades into the space between galaxies. Feel the weight of your legs now, heavy against the mattress, as though the day's motion has finally settled into stillness. Let that heaviness spread upward, into the hips, the lower back, each part sinking a little deeper with every breath. Your arms grow dense and still, resting at your sides like something set down after a long carry. Even your head feels weighted now, cradled fully, needing nothing to hold it up. Let it all sink, layer by layer, into rest. Dark matter forms an even larger halo, invisible and silent, wrapped around everything we can actually see. It emits no light, reflects nothing, and passes through ordinary matter without a trace. Its presence is known only through gravity, the way it tugs on stars and bends their paths. This unseen shell extends far past the stellar halo, cradling the entire visible galaxy within its quiet reach. Yet its mass tells a startling story. The dark matter halo outweighs every star, every cloud of gas, everything we can see combined. Some estimates suggest it holds several times more mass than the visible galaxy altogether. The Milky Way we observe, its stars, its dust, its glowing arms, may be only a small, luminous fraction of something far larger surrounding it in the dark. Rotation curves reveal the presence of dark matter, though the matter itself remains unseen. Stars near the outer edge of the Milky Way move almost as fast as those closer to the center, which should not happen if only visible matter shaped their paths. In the 1970s, astronomer Vera Rubin measured these speeds and found gravity's fingerprint reaching far beyond the galaxy's glowing disk. Something unseen was holding the outer stars in their swift, steady orbits. The dark matter halo has no clearly defined outer edge, fading rather than stopping. Its density thins with distance, blending into the surrounding dark without any visible boundary. Cosmologists still debate exactly where the halo's influence finally ends, since its pull grows too weak to measure long before it disappears entirely. The Milky Way, in this sense, has no true border at all. Streams of stars trace disrupted dwarf galaxies scattered through the halo's dark reaches. Long ago, smaller galaxies wandered too close to the Milky Way and were slowly pulled apart by its gravity. Their stars now stretch into thin, curving rivers across the sky, remnants of galaxies that no longer hold together. Each stream is a kind of memory, a shape left behind after something whole came undone. The Sagittarius stream wraps around the Milky Way like a loose, glowing ribbon. It circles our galaxy in a long, looping path, made of stars torn from a smaller companion galaxy over billions of years. Astronomers first traced its shape by mapping the positions of thousands of scattered stars. Seen from far above, the stream would appear as a pale, wide loop, curving past our galaxy's outer edge. The Sagittarius dwarf galaxy is being torn apart by our galaxy's gravity, piece by piece. Each pass through the Milky Way's disk pulls more of its stars loose, stretching them into long, trailing arcs. What remains today is only a fraction of what this dwarf galaxy once held. In time, its last stars will scatter completely, absorbed into the Milky Way's own vast structure. Globular clusters orbit within the galactic halo, tracing wide paths far above and below the disk. Unlike the halo's scattered individual stars, these clusters travel together, tightly bound by their own gravity. Their orbits carry them high over the galaxy's plane and back again, journeys that can take hundreds of millions of years to complete. Each cluster moves like a small, self-contained galaxy of its own. Omega Centauri stands as the largest known globular cluster in the Milky Way. It holds so many stars packed so densely that early astronomers once mistook it for a single star. It may once have been the core of a small galaxy. its outer layers stripped away by the Milky Way's gravity, a question astronomy has not fully settled. Its light, seen from Earth tonight, still carries the shape of that earlier larger galaxy. Globular clusters can contain hundreds of thousands of stars, all bound within a space just a few tens of light-years wide. Near a cluster's center, stars crowd so closely together that their combined light can outshine an entire small galaxy. From within such a cluster, the night sky would blaze with countless nearby suns, far brighter than anything visible from Earth. Yet even there, order holds, each star following its own steady gravitational path. Somewhere beyond the room, a low hum rises and fades, a settling house or wind moving against the window far off. Let it arrive without needing anything from you, and let it pass the same way, without effort. Sounds like this have always moved through the dark, arriving, lingering, drifting on, asking nothing of whoever hears them. Let your breath find that same unhurried rhythm, arriving, lingering, drifting on. There is only this moment, this hum moving through it, and you resting beneath it all. Globular cluster stars are among the oldest known objects in the universe. Many formed more than 12 billion years ago, not long after the galaxy itself began taking shape. Their light tonight has traveled across nearly the entire age of the cosmos to reach us. Looking at one of these ancient stars means looking back toward the universe's earliest chapters, still burning steadily in the present sky. 47 Tucanae glows as one of the brightest globular clusters visible from Earth. Southern Hemisphere skies reveal it as a soft smudge of light, though within that smudge lie hundreds of thousands of stars. Its dense, spherical shape has drawn astronomers' attention for centuries, curious about how such a tight gathering of suns could hold together for so long. Tonight, its old light still reaches us, steady and unbroken. A number of globular clusters may be the remnants of smaller galaxies the Milky Way once absorbed. Their stars sometimes carry chemical signatures unlike those born within our own galaxy, hinting at a different origin. Over billions of years, gravity may have stripped away a dwarf galaxy's outer layers, leaving only its dense stellar core behind. What orbits our galaxy now may once have belonged to something else entirely separate. Roughly 150 known globular clusters orbit within the Milky Way. Each one drifts on its own long, looping path, some staying close to the galactic disk, others venturing far into the outer halo. Together, they form a kind of scattered constellation of ancient star cities, each holding its own history. Astronomers continue searching the dustier regions of the sky, expecting a few more clusters still remain hidden. Each cluster moves through 3 dimensions, tracing wide, looping paths above, below, and through the galactic plane. Unlike the orderly disk of stars near the Sun, these orbits carry clusters far above and beneath the galaxy's flattened shape. Some rise high into the halo, before curving back inward, taking hundreds of millions of years to complete a single loop. Their motion traces the galaxy's gravity in 3 full dimensions, not just one flat plane. Far beyond the visible stars, the halo's outer reaches blur gradually into the emptiness between galaxies. There is no clean boundary where the Milky Way ends and intergalactic space begins. Instead, the density of stars simply thins with distance, fading until it becomes indistinguishable from the surrounding dark. The galaxy, seen this way, has no true edge at all, only a slow and gentle dissolving. Hypervelocity stars race outward, flung from the crowded region near the galaxy's center at extraordinary speed. Unlike most stars, which circle the galaxy in stable, looping paths, these travel fast enough to eventually escape the Milky Way's gravity altogether. A handful have been tracked speeding away at velocities exceeding 1,000 kilometers each second. Somewhere far from here, one of these stars is still moving outward, alone. Their origin may trace back to close encounters near the supermassive black hole at the galaxy's heart. A star drawn too near a binary system, or caught briefly by the black hole's gravity, could be flung outward at tremendous speed. The physics remains difficult to observe directly, since such events likely happen only rarely across cosmic time. Still, the escaping stars themselves stand as quiet evidence that something dramatic once occurred. Astronomers estimate the Milky Way's total stellar mass at around 60 billion times the mass of the Sun. That figure accounts only for the stars themselves, not the gas, dust, or invisible dark matter woven throughout the galaxy. Even so, 60 billion solar masses represents an almost unimaginable amount of nuclear fire, spread across 100,000 light-years of space. Every star contributing to that number still shines somewhere above us tonight. The Milky Way holds somewhere between 100 billion and 400 billion stars. The exact number remains uncertain, since dust and distance hide many stars from even our best instruments. Whatever the true count, it means more stars exist in our galaxy alone than there are grains of sand on many an earthly shore. Each one, distant and small from here, is its own sun to someone's sky, somewhere. Let warmth begin somewhere small, perhaps the center of your chest, and let it spread outward from there. Feel it move into your shoulders, loosening what they've carried all day, then down through your arms to your fingertips. Let it settle into your stomach, your hips, your thighs, sinking lower with each breath. By the time it reaches your feet, your whole body may feel warm all the way through, heavy, unhurried, held. Red dwarfs make up the vast majority of stars in the Milky Way, though none are bright enough to see without a telescope. Cool and small, these stars burn their fuel with remarkable economy, some destined to shine for trillions of years. Their dimness kept them hidden from early astronomers, who judged the galaxy by its brightest members. In truth, the galaxy's most common star is one we rarely notice. Stars like our Sun turn out to be far less common than once assumed, forming only a modest slice of the galaxy's stellar population. Yellow dwarfs occupy a narrow middle ground between the tiny red stars and the rarer giant. This rarity gives the Sun a kind of quiet distinction among its neighbors. Even so, it remains an ordinary star, unremarkable except for what orbits around it. Planets appear to be as common as stars within the Milky Way, with billions estimated to exist across the galactic disk. Many are thought to be close to Earth's size, rocky and modest, circling stars far too distant to name. Astronomers cannot see most of these worlds directly, only infer them from tiny dips in starlight. The galaxy, it seems, is quietly crowded with small, round worlds. Surveys using space telescopes suggest billions of planets may sit within the temperate zones where liquid water could exist. Such worlds neither too close nor too far from their stars, warmed just enough to hold on to an ocean. The true number remains an estimate, drawn from statistics rather than direct sightings. Still, the possibility of so many gentle, watery worlds gives the night sky a certain hopeful hush. When every star, planet, gas cloud, and unseen particle is added together, the Milky Way's total mass reaches somewhere between 1 and 2 trillion times that of the Sun. Most of this mass takes the form of dark matter, a substance that neither shines nor reflects light. Its presence is known only through gravity's quiet influence on everything else. The galaxy, weighed in full, is far heavier than its stars alone reveal. Smaller galaxies circle the Milky Way, the way moons circle a planet, held loosely by gravity across enormous distances. Some orbit close, their stars mingling faintly with our own. Others drift much farther out, tracing slow paths that take hundreds of millions of years to complete. Each satellite carries its own smaller family of stars, bound for now to our galaxy's greater pull. Among the Milky Way's companions, the large Magellanic Cloud shines as one of the brightest satellites visible from Earth. Its stars form a loose, irregular glow rather than a tidy spiral. Rich in gas, It continues forming new stars even as it circles our galaxy. Sailors once used its light for navigation, long before its true nature as a separate galaxy was known. Nearby, the small Magellanic Cloud follows a similar path, tied gravitationally to its larger companion. The two dwarf galaxies drift together, connected by streams of shared gas and a long history of mutual pull. Smaller and fainter, this companion still holds hundreds of millions of stars within its modest boundaries. Together, they form one of the sky's most familiar southern sights. From the southern hemisphere, both Magellanic Clouds appear as soft smudges of light, visible without any instrument at all. Ancient peoples across the southern world included them in their stories long before telescopes existed. Their glow resembles distant, torn pieces of cloud caught among the stars. On a clear night far from city lights, they remain one of the simplest wonders to find overhead. Trailing behind the Magellanic Clouds stretches a long ribbon of gas known as the Magellanic Stream, pulled loose by the Milky Way's gravity. This stream stretches across a vast portion of the sky, invisible to the naked eye, but detectable in radio waves. It likely formed as tidal forces, slowly stripped gas from the smaller galaxies during their long approach. The stream stands as a quiet record of a very slow cosmic embrace. Let the breath settle, like smoke rising from a candle just blown out, thin and pale, curling upward before it thins into nothing. There is no shape to hold, no path to follow. It simply rises, spreads, and disappears into the dark air above. Let your thoughts do the same tonight, rising, thinning, dissolving, until only stillness remains where they used to be. The Magellanic Clouds may be sweeping past the Milky Way for the very first time. Careful measurements of their motion suggest they are moving too fast to be gravitationally bound in a long, repeating orbit. If that is true, this could be their first close approach after billions of years of separate wandering. Astronomers continue refining these velocities, but the picture hints at a slow, singular encounter rather than an old, familiar dance. Toward the constellation Canis Major lies a strange clustering of stars called the Canis Major overdensity. Its stars sit slightly apart in age and motion from their surroundings, hinting at an origin outside our galaxy's usual disk. It may represent the remains of another dwarf galaxy, pulled apart long ago by the Milky Way's gravity. Its stars now drift scattered and thin, folded quietly into our galaxy's outer disk. Dozens of small companion galaxies circle the Milky Way at varying distances, most too faint to notice without careful searching. They range from loose collections of a few thousand stars to fuller dwarf galaxies holding millions. Each one traces its own long, looping path through the darkness surrounding our galaxy. Together, they form a quiet entourage, faint and patient, bound loosely by gravity across enormous stretches of empty space. Ultra-faint dwarf galaxies rank among the dimmest galaxies ever detected. Some contain only a few hundred stars, spread thin across a surprisingly large volume of space. Their faintness makes them nearly invisible, even with large telescopes, discovered only through careful surveys of subtle stellar clustering. Despite their dimness, they may hold clues to the earliest, smallest structures that formed after the universe's beginning. Draco and Ursa Minor, two small satellite galaxies, have circled the Milky Way for billions of years. Both are ancient, holding stars far older than the Sun, formed when the universe itself was young. Their populations show little sign of recent star birth, suggesting long, quiet histories with little disturbance. They orbit like old companions, faint and steady, carrying the memory of an early universe within their dim starlight. Over immense stretches of time, the Milky Way is expected to slowly absorb several of its smaller satellites, Gravity tugs steadily at their loose structures, stretching them into thin streams before they merge fully into our galaxy's halo. This process has likely repeated many times across the Milky Way's long history. Each merger adds new stars, new motion, and new history, folded gently into the larger galaxy's ongoing story. Two galaxies rise above all others in our cosmic neighborhood, the Milky Way and Andromeda. Both are large barred spirals, each holding hundreds of billions of stars within sweeping disks of gas and dust. They anchor the surrounding region with their combined gravity, shaping the motion of every smaller galaxy nearby. Compared to their many small companions, these two stand as the true giants of the local group. Beyond these two giants, the local group holds more than 80 known galaxies of every size and shape. Most are small, faint dwarfs, easily overlooked beside their larger neighbors. Together, they form a loosely bound cluster, drifting slowly through space under one another's mutual pull. It is a modest gathering by cosmic standards, yet within it lies nearly everything familiar to us in the night sky. Andromeda's light travels roughly 2.5 million years before reaching our eyes. It stands as the most distant object easily visible without a telescope, a faint smudge for anyone patient enough to find a dark sky. The light you might see tonight left its stars long before humans existed at all. Across that vast gap, Andromeda glows steadily, patient and unaware, waiting quietly at the edge of what we can see unaided. Andromeda and the Milky Way are drawing nearer to each other with every passing year. Each galaxy moves through space at hundreds of kilometers per second, pulled by their mutual gravity across the dark gulf between them. Astronomers measured this approach using tiny shifts in Andromeda's light, a method that revealed motion invisible to the eye. For now, the two galaxies simply glide toward a distant future meeting, unhurried across unimaginable spans of time. Let your jaw loosen now, just slightly, as if it forgot what it was holding. Let your eyelids grow heavy, thick as warm cloth, resting without effort. Behind them, notice only darkness, wide and unmarked, asking nothing of you. There is no picture to hold there, no shape to follow, just that dim, spacious dark, spreading gently behind your closed eyes, while your face rests, unguarded, into the pillow beneath it. Roughly 4.5 billion years from now, astronomers expect Andromeda and the Milky Way to finally collide. The event will unfold across hundreds of millions of years, far too slow for any single eye to witness as a single moment. Stars will rarely strike one another directly, since the space between them remains so vast. Instead, gravity will reshape both galaxies gradually, weaving their stars and gas into something new. The Triangulum galaxy holds the position as the third largest member of our local group. Smaller than both the Milky Way and Andromeda, it still spans tens of thousands of light years, filled with its own spiral arms and star-forming regions. Some evidence suggests it orbits Andromeda much as a smaller companion trails a larger partner. Even at its modest size, Triangulum adds its own quiet contribution to the shared gravity binding our galactic neighborhood. Gravity holds the local group together, drawing its member galaxies inward across millions of years. Unlike the wider universe, which stretches ever outward, this small cluster resists that expansion through its own mutual pull. Each galaxy's motion bends slightly toward the group's shared center of mass. Over unimaginable stretches of time, this collapse continues, patient and unbroken, folding the group ever closer upon itself. Most galaxies within the local group are small dwarf ellipticals, or irregular clusters of stars, far outnumbering giants like the Milky Way. These modest galaxies often contain only a few million stars, scattered loosely without any defined spiral shape. Many appear faint and shapeless when viewed through a telescope, easily missed beside their brighter neighbors. Yet each one carries its own history of formation, motion, and slow change across billions of years. From edge to edge, the local group stretches across roughly 10 million light-years of space. Within that span sit dozens of galaxies bound loosely by gravity, separated by vast stretches of near emptiness. Light crossing this distance would need 10 million years to complete the journey. Even at such scale, the local group remains only a small corner within the far larger architecture of the universe. Zooming further outward, the local group itself resides within a much larger structure called the Virgo supercluster. This vast collection gathers thousands of galaxies, clusters, and groups across an immense region of space. Our entire galactic neighborhood makes up only a small piece within this greater framework. Seen from such distance, even the Milky Way becomes a single point among countless others, woven into something far bigger than itself. At the heart of this supercluster lies the Virgo cluster, whose immense gravity anchors the surrounding structure. Containing over 1,000 galaxies, it exerts a steady pull that shapes the motion of galaxies far beyond its own boundaries, including our own local group. This distant cluster, though never visible to the unaided eye, quietly influences the trajectory of everything nearby. Its gravity reaches across tens of millions of light-years, binding a vast neighborhood together. The Milky Way itself is a barred spiral galaxy, one among billions of galaxies scattered throughout the observable universe. Its curved arms, glowing bulge, and central bar mark it as a fairly typical example of its kind. Countless other galaxies, near and far, share this same general shape, each holding its own stars, planets, and stories. Our galaxy, remarkable as it feels from within, is simply one voice among an immense cosmic chorus. Spiral shapes turn out to be common among the bright galaxies near us, making up roughly 2/3 of what astronomers survey in nearby space. Ellipticals and irregulars fill out the remainder, each with their own quieter story. Our galaxy's curved arms and glowing disk place it firmly among the majority pattern of the visible universe. Being ordinary in this sense is its own kind of belonging. Zoomed out far enough, the Milky Way belongs to something larger still, a structure named the Laniakea supercluster. Within this vast gathering, our galaxy is one thread among many, pulled along a shared gravitational current. The name itself means immeasurable heaven, drawn from Hawaiian language to honor its scale. Everything nearby, including the Virgo cluster, moves as part of this same slow drift. Feel the breath settle into its own rhythm now, arriving and leaving without any effort from you. Notice how the exhale lasts a little longer than the inhale, and let it stay that way. Each breath draws in, holds for a moment, then releases further into the mattress beneath you. There is no pace to keep, no count to reach. Just this breath, then the next one, unwinding a little more each time. Laniakea itself stretches across roughly 500 million light-years, a distance that dwarfs even the local group many times over. Within that reach sit around 100,000 galaxies, all responding to the same gravitational pull. The Milky Way rides along near one edge of this enormous basin, carried by a current too vast to notice from within. Scale at this level begins to lose its ordinary meaning. Superclusters like Laniakea are not scattered at random, but arranged along filaments, long threads of galaxies stretching across the darkness between them. These filaments form the skeleton of the universe, tracing paths where matter gathered early in cosmic history. Galaxies cluster densely where filaments cross and thin out where they stretch alone. The pattern resembles something almost organic, though built from gravity alone. These filaments and the galaxies strung along them form what astronomers call the cosmic web, linking distant regions across enormous stretches of emptiness. Vast voids sit between the strands, regions nearly empty of galaxies altogether. Light traveling from one filament to another may cross these voids for hundreds of millions of years. The universe, seen this way, resembles a loose net cast across the dark. Within the observable universe, the Milky Way is one among trillions of galaxies, each holding its own stars and stories. Deep sky surveys have counted galaxy after galaxy in patches of sky no larger than a grain of sand held at arm's length. Extending that density across the entire sky suggests a number too large to picture comfortably. Our galaxy is simply one small light among an uncountable multitude. Galaxies themselves began forming remarkably early, within the first few 100 million years after the Big Bang. Clumps of gas and dark matter collapsed under their own gravity, sparking the first generations of stars. Telescopes peering toward the earliest cosmic light have found faint young galaxies already glowing in that primordial dark. From these humble beginnings, structures like our own eventually took shape. The Milky Way itself likely began forming around 13.6 billion years ago, not long after the universe's earliest galaxies appeared. Its oldest stars, found scattered through the halo, still carry traces of that ancient beginning. Over billions of years, smaller clumps of gas and stars gradually gathered and merged into the structure we now inhabit. Our galaxy's history reaches back almost to the dawn of everything. Hidden within the motions of ancient stars lies evidence of a long-ago collision, a merger astronomers called the Gaia-Enceladus event, a dwarf galaxy torn apart by the Milky Way's gravity billions of years ago left behind stellar streams still traceable today. These stars move on paths distinct from their neighbors, carrying the fingerprint of that ancient union. Long after the encounter itself faded, its signature remains written across the sky. That ancient collision, the Gaia-Enceladus merger, left more than moving stars behind. It puffed up the Milky Way's thick disk, thickening it with stars kicked into higher, wider orbits. Before the encounter, our galaxy's disk was thinner and calmer. Afterward, it carried a taller layer of older stars, still measurable today. That single long-ago event helped shape the very structure surrounding our solar system now. Long stretches of time gave the Milky Way its familiar spiral shape. Billions of years of gas falling inward, stars forming, and smaller galaxies merging gradually built the arms we see swirling through images today. No single moment created this structure. Instead, countless small additions layered atop one another, slowly sculpting order from what began as scattered clumps of gas and starlight. Even now, small satellite galaxies keep feeding the Milky Way with new stars. As dwarf galaxies drift close, gravity pulls at their edges, stripping away stars and gas that eventually join our galaxy's disk and halo. This process never fully stopped. Our galaxy is, in a sense, still being built, gathering fresh material from smaller neighbors caught within its gravitational reach. Let your body grow heavy now, one part at a time. Feel your feet settle deeper into the mattress, heavier than a moment ago. Let that heaviness rise into your calves, your knees, sinking further with each breath. Your hips grow still, your back grows still, pressing down into the warmth beneath you. Shoulders loosen and drop. Even your hands feel weighted, resting exactly where they lie. Far ahead in time, the Milky Way is expected to merge completely with Andromeda, forming a single combined galaxy some astronomers have nicknamed Milkomeda. The two galaxies, already drawing closer, will eventually pass through one another repeatedly before settling into one shape. Stars rarely collide directly during such mergers. Instead, gravity reshapes their paths, weaving two galaxies into a single, larger structure over great stretches of time. Once fully merged, the resulting galaxy will likely lose its spiral shape entirely, gravitational disruption tends to scramble orderly orbits, turning graceful spiral arms into a smoother, rounder form known as an elliptical galaxy. No cometa may end up glowing softly, without arms or a defined disk. Its stars settled into looser, more randomized paths after the long process of merging concludes. As galaxies merge, the sky itself will change. Andromeda, already visible as a faint smudge tonight, will grow larger and brighter over millions of years, eventually stretching across a wide portion of the heavens. Later generations, if any remain to watch, might see two galactic cores drifting closer together, reshaping familiar constellations into something entirely unrecognizable from what we know now. Long before any such merger unfolds, star formation across the Milky Way will steadily slow. Galaxies need fresh gas to build new stars, and that raw material is finite. As reserves are used up and not replenished quickly enough, fewer new stars will ignite. The galaxy will gradually dim, its bright, youthful regions fading as older stars come to outnumber the newly born. Our own sun will not witness any galactic merger. Long before Andromeda and the Milky Way draw close, the sun will exhaust its hydrogen fuel, swelling into a red giant and later fading into a white dwarf. That transformation is expected roughly 5 billion years from now, arriving well ahead of the galaxy's eventual collision. The sun's story will end long before our galaxy's next chapter begins. Even as all this unfolds, the Milky Way's rotation will keep evolving. New material falling in from mergers, streams, and satellite galaxies will subtly shift how the disk spins and how mass is distributed throughout it. Rotation is never truly fixed. It responds, over immense stretches of time, to everything the galaxy absorbs, adjusting gradually as our galaxy continues its long, unfinished formation. Beyond Laniakea, gravity keeps organizing matter into even grander patterns. Clusters of galaxies gather into clusters of clusters, and those larger groupings hint at structures so immense that light itself needs hundreds of millions of years to cross them. Cosmologists studying these superclusters believe they may be part of unnamed systems, still too vast for any single survey to fully map. The observable universe reaches about 93 billion light-years from edge to edge. That number describes not what we can see directly, but the space light could have crossed given how the universe has stretched since its beginning. Beyond that boundary, more universe likely exists, simply out of reach of any signal that could ever arrive here. Fill the space beyond every galaxy, cluster, and void, and you find a faint radiation bathing the entire sky. Cosmic microwave background light reaches Earth from every direction equally, a near-uniform glow first detected by accident in the 1960s. It carries no images of stars, only a whisper of heat left over from the universe's earliest moment. That whisper is the afterglow of the Big Bang itself, visible in every direction we look. It was released when the universe cooled enough for light to travel freely, roughly 380,000 years after everything began. Looking at it means looking at the oldest light there is, a picture of the cosmos in its infancy, still arriving tonight. Somewhere far off, a low hum seems to rise and fall, like wind moving through an old house settling into itself. It comes and goes without asking anything of you. You don't need to find its source or follow it anywhere. Let it pass by the way distant sound always does, arriving softly, fading again, leaving the room a little heavier, a little warmer, a little closer to sleep. Zoom far enough out, and the universe stops looking scattered and starts looking woven. Galaxies gather along long filaments, threading through enormous empty voids like beads strung on invisible string. This structure, often called the cosmic web, took billions of years to form from tiny variations in the early universe's density, growing under gravity's steady pull. Something invisible is pushing everything apart faster than gravity alone would allow. Astronomers call it dark energy, though no one yet knows precisely what it is. Its effect was discovered in the late 1990s through observations of distant exploding stars that appeared dimmer than expected, revealing an expansion that speeds up rather than slows down. Distant superclusters, already separated by staggering distances, will keep drifting farther apart as expansion continues. Over unimaginable spans of time, some now visible to us will slip beyond the reach of any future observer's light. Space itself carries them away, not through motion within it, but through the fabric between them steadily growing. The Milky Way's ultimate fate is bound to this same expansion, even as its nearby merger with Andromeda proceeds on its own timeline. Locally, gravity still wins, drawing galaxies together into the combined system, sometimes called Milkomeda. But on the largest scales, that merged galaxy will drift ever farther from everything beyond its immediate neighborhood, adrift in a universe growing emptier around it. Across the wider universe, star formation will fade as galaxies gradually use up their reserves of gas. New stars need raw material to ignite, and that material is finite everywhere, not only within our own galaxy. Trillions of years from now, most galaxies will hold only the dim embers of stars born long before, their brightest chapters already behind them. Beyond the local group, entire clusters will eventually cross an invisible threshold, their light stretched into darkness before it ever reaches us. Expansion carries them past the horizon of what any future eye could see. From here, the sky will empty gradually, supercluster by supercluster, until only the galaxies bound to us by gravity remain visible, holding their ground against the widening dark. Andromeda, the Milky Way, Triangulum, and their smaller companions may stay knotted together by gravity long after the wider universe drifts away. This is the local group's quiet advantage. It is dense enough, close enough, to resist the pull of expansion. While farther galaxies vanish beyond reach, this small cluster of light may remain a companionship, unbroken by the emptiness spreading around it. The merged galaxy born from the Milky Way and Andromeda, the one sometimes called Milkomeda, may endure for trillions of years afterward. Its stars will keep circling long after the collision settles, tracing slow orbits through a structure reshaped but not destroyed. Time on this scale is difficult to hold in the mind, yet the galaxy itself will simply keep turning, patient beyond any human measure. As the eons pass, ordinary stars will fade one by one, and the mass that remains will belong increasingly to their remnants. White dwarfs, neutron stars, and black holes, cold and dense, will outnumber the living stars that once outshone them. The galaxy will grow dimmer, not because it disappears, but because its brightest voices gradually fall silent, leaving only quiet, gravitational presences behind. Cosmologists describe one possible ending for everything as heat death, a state where energy spreads so evenly that nothing more can happen. Stars will have burned out, black holes will have evaporated over inconceivable spans, and temperature differences, the very engine of change, will fade to nothing. It remains an open question whether this is truly the universe's final chapter, but the physics points gently in that direction. And so the story of the Milky Way becomes, in the end, a story about scale, about how one small system of stars can hold both a home and a horizon within it. You have spent this time learning the shape of the galaxy that carries you quietly around a center 26,000 light-years away. Let that be enough for tonight. Rest now inside a galaxy still turning gently beneath you. Good night.